we're talking about functions. All this whole unit's about functions. So we get now to really the last couple of modules that are left before the test. You'll have a test next week on all the function stuff. But in lesson 4.1, we're going to look at specific functions. And they do have a great amount of application. And we're going to look at some new terminology that you're going to need to know, and functions that can be defined in a couple of different ways. But today we're going to look at sequences and what they look like. We're just going to get a good start on that. So our standard here is to recognize that a sequence is a function and that we can define it recursively. That's a crazy word, isn't it? Whose domain is a subset of the integers. Now that sounds complicated, but it's really not. Okay? Especially that part about whose domain is a subset of the integers. Basically, all we're saying is this. In a sequence, my domain is going to be, here's the first term, that's domain 1. Here's the second term, domain 2. Here's the third term, domain 3. And it'll be that simple. Well, let's get some definitions down first. You need to copy this down. A sequence is a list of numbers in a specific order. Each element in a sequence is called a term. Well, we're kind of used to terms in algebraic expressions, but now we're going to call each position, each element in this sequence a term as well, and that kind of makes sense, I think. In a sequence, each term has a position number. So in this sequence, 7, 9, 11, 13. The first term is 7. Pretty simple. Second term is what? 9. The third term is 11, and the fourth term is 13. So the position number is where it falls in the sequence. So we're going to look at that in terms of a real problem. Okay? So a go-kart racing track charges $5 for a go-kart license and $2 for each lap. All right, so if we list the charges for 1 lap, 2 laps, 3 laps, and so on, in order, the list forms a sequence of numbers. So, in other words, the first time we go around, we're pigeon forwards and we're going around and they're going to charge us per lap. That'd be kind of expensive, wouldn't it? So just to get in the golf cart or the go-kart, we're going to pay $5. Then we go around one time, it will cost us $7 for our first lap. Now, they're not going to charge us, for not taking a lap, so the first charge is actually $7 for the first lap. Then the next lap is $9, because they've already charged us the 5, they charged us the first lap, now they charge us for the second lap. And then the next one is 11. The next one is 13. Let me ask you a question. In this sequence, Alejandro, I'm going to call on you, sir, so get ready. In this sequence, what is happening? What is happening? Alejandro? Alejandro, I've called on you and you're not answering, my friend.
Yeah.
Oh, he's there. Yay. Scared me to death. All right, so what's going on, man, with this sequence? It starts at 7, then the next one's 9. What pattern do you see?
It's skipping by 2s.
Yes, exactly. It's just increasing by 2. Well, that's pretty simple, really, isn't it? Every time I take a lap, they're going to charge me $2 more. It's very much a function and very much a sequence, okay? So check it out. The position number here, then, is the term of that sequence. So we've already said that the first lap cost us $7, and the second lap's 9. So then we get to the third lap, and the third lap will be $2 more, which is 11. And the fourth lap is 13. The fifth lap will be 15, sure. And the sixth lap is 17. Do you see That's the same thing as the functions we've been talking about, except now our domain's real simple. Our domain is simply the position of each term. The domain, this is my first lap, my domain of 1, or my X input value of 1. Remember, input, domain, independent variable, those all mean the same thing. So my domain here is simply the position number. All right, so I can write that in a function term saying f of 1 is 7, or f of 3 is 11, f of 6, 17, or f of 4 is 13, or f of 5 is 15. Just looking at the function notation, I can tell that if I look at, what is f evaluated for? F of 4. Well, that's going to be $13. So all I've done is taken this sequence, and because a sequence does form a function, I'm writing in function notation. Now, one thing about sequences that I want you to know, we'll look at this a little bit more tomorrow, but sequences can be written also in a function notation with subscripts. What I mean by that is, you might want to write this down underneath, this same sequence where I had f of 1 equals 7, you might see it as a sub 1 equals 7. That's the same thing. It's just a different way to write a sequence. Sometimes we write a sequence with subscripts just so it's different looking than function notation. So that means, when f of 6 was 11, then my subscript notation here is a of 6 equals 11. It's the same thing, so don't let that mess you up or throw you off or anything like that. That part's easy. For our purposes in this lesson, we're going to primarily look at it in terms of function notation, but understand those two are interchangeable as well. Okay? So looking at this function, there's a couple questions here. Shaylin, identify the domain of that function of e. Yes.
1, 2, 3, 4, 5, 6.
Yeah, awesome. 1, 2, 3, 4, 5, 6. Now, let's think reasonably and logically here. The domain is 1, 2, 3, 4, 5, 6. Question. Is there any limitation to the number of laps I can ride? You what?
No. 6.
No,
Just keep going.
it's saying the problem? I don't think
No,
it
I
said.
was trying to say.
Go-kart, yeah, here's the problem. Go-kart, racetrack, church, 5 hours, 1, 2, 3, and so on. Okay? So, we could probably run 100 laps if we could afford it, right? So when I go to write my domain, I want to indicate, and I can use an ellipsis to indicate that it goes on, or I could say it this way. I could say that n is greater than or equal to 1. In other words, all numbers, my domain starts at 1, but it's just reasonable to say that domain continues on out forever and ever. I guess I could ride till I run out of gas, but we don't have any way of knowing that mathematically. And then probably somebody would come running out with a gas can and fill it back up, so we could keep riding after that. What's the range of this function? Now that's a little,
7.
right? It's 7. What else?
9, 11, 13, 15.
Yeah, 9, 11, 13, 15, 17, and could it go on?
19, 20.
How could I write that to indicate that it goes on symbolically?
Like 2,
By twos, okay. What's happening here? Let's see. We could say that the range, okay, what do you notice about 7, 9, 11, 13, 15? Those are, what kind of numbers are those?
What number?
They're kind of like my tie, they're odd numbers, right? Okay, and so they're odd numbers, so the range is odd numbers. And we could say, and maybe we should say odd integers. That would be a little more mathematical, wouldn't it? Yeah, because it's not decimals. Odd integers such that n is greater than or equal to 7. So we can write out in words that way. Starting with 7, it's going to be odd integers. Well, that'll work. We understand what our domain is, what our range is. That's pretty simple. So in context, what does f of 4 equals 13 mean? I'll ask, let's see, who can I pick on here? We'll go to Carlos. Carlos, my friend, what does it mean when I say f of 4 equals 13? Based on this problem we've been doing here. Do you know? Can you hear me? Yeah.
Wait, can you say that again?
Sure. When I say the function of 4 equals 13, in relationship to this golf cart problem we got here, okay? What does that mean? What is the 4? The 4 is how many what? Somebody help me. It's how many laps, okay? So in context, this function f of 4 means 4 laps will cost us how much? I'll let you chime in there. Somebody help me. Yeah, $13. I think your computer's freezing up just a little bit at home, but it's okay. You did good. Thank you so much. And then it says, well, how do we find the missing values in the table? Well, we got to write that sequence down, correct? How do we find the missing values back here? How did I find this when I filled them in and read? What did I do? Yeah, counted by 2. In other words, these are increasing by 2 each time. And I knew that my domain, one of the things about sequences, my domain is always going to be 1, 2, 3, 4. It's the position of the sequence. All right? So the domain is just simply going to be naming the position of the sequence. So why is it that this positional number, the first number, second number, third number, why is it that the corresponding terms of that sequence can be considered a function? Why do you think that is? Going back to this for a second. Why is this a function?
Is the range determined sequence? Because there's not 2 input, like there's not one same output that has 2. Wait.
Yeah.
There's not one input that has 2 outputs.
Yeah, you got the right idea here. What you're saying is each time in my sequence, each position number has a unique, right, number in the sequence. There are no repeats in the range. We don't have any repeats in the domain. I really should have said domain there. We have nothing repeating there. In other words, if we're on the 3rd lap, okay, Kiara rode the 3rd lap, I rode the 3rd lap, and I get off the go-kart, and she gets off the go-kart, and they charge her $11, and they charge me $21. Would that be fair? No. That's why it's a function, okay? Because the number of laps creates a unique charge, a single, one and only charge. Good deal. Now, we can write what we call an explicit rule. You need to write this down, this definition. Explicit rule for a sequence defines the nth term as a function of n for any whole number n greater than 0. In sequences, it makes sense that we don't have a 0 term. We can't have a 0 lap, can we? So explicit rules can be used to find any specific term in a sequence without finding any of the previous terms. Basically, an explicit rule is just a function rule. Notice this problem I have here. I've written it in both ways. I've written it as f of n equals n squared plus 2. Remember also that I can write it in subscript notation as well. The good thing on the EOC, you'll be given formulas for sequences, and that's kind of nice. I'll be giving you some formulas tomorrow for you to remember, but or to write down, but you can refer back to your notes. On the test, I'll give you the formula as well. So if I want to find the first 4 terms of this sequence, okay, f of n equals n squared plus 2, the way I'm going to do it is I'm going to do a t-chart. And it doesn't matter which notation I use. I could say n and a sub n. I could do it like that. It doesn't matter. And as for the first 4 terms, so it's just simply 1, 2, 3, 4, like that. And then I substitute in the math, okay? For example, let me clear my little space here. If n's 1, then it's 1 squared plus 2, which is 3, right? So my first one is 3. If it is 2, then it is 2 squared plus 2. So that's 4 plus 2, which is 6. If f is 3, then it is 3 squared plus 2. So that's 9 plus 2, or 11. And then if it's 4, it's 4 squared plus 2, or 18. So the first 4 terms of this sequence, we could write those as 3, 6, 11, and 18. Is that hard? So if that's the case, and I asked you to find the 20th term, how would you do that? I'll call on somebody in the room. I won't put my own one. Okay, Shayla's got it. Yes.
You keep going until you get to 20.
You could. Shaylin said, hey, I could just keep going till I get to 20. And I'm glad you said that. In fact, had I could have, I would ask you to say that, because that's a recursive way of doing it, okay? So in other words, we keep moving on and we get each term, but I'm going to let Kiara steal the thunder here. What do you think?
Put it in the formula thing.
You put it in the function. Yeah, that'll save you having to. This is an explicit rule, right? So I could go on and do 5, 6, 7, 8, 9, 10. But if I go straight to the explicit rule of the function and say, okay, what's f of 20? Okay, that's just going to be 20 squared plus 2.
Couldn't you do 3 times 20?
Do what?
Couldn't you do 3 times 20?
I'm sorry, I'm missing your question. What now? Okay. I mean, I may not be understanding what you're. I know I'm not understanding what it is. 20 squared is 400 plus 2. So my function at 20 is 400 and what? 10. Does that make sense? I I sense that that there's something that's not clicking. What is it?
No,
That's good? Okay, good. I just want to make sure before I move on. Any questions? I really like the explicit rule for finding a sequence. I just think it's easy. You really just plug it in. So here's a problem for you real quick. And this one is for you to do. So write the first 4 terms of this sequence, and it's defined by this explicit rule. Okay, I'll give you about 3 minutes.
Wait, do we just start at 1?
Do what?
Do we just start at 1?
Yeah, because remember, a sequence is in order of the terms. So you always have your first term, position 1, position 2, 3. All sequences will start with 1, which is another thing I like too. All right, so give me the first 4 sequences. So the first term then, f of 1, is 1 squared, which is 1, times 3 plus 1, which is 4. So f of 1 is 4. So my first term of the sequence is 4. All right, so we got to get the second term. Does somebody else, Louise, help me with the first one? Somebody want to help me with the second one? What did you guess, me? 13. Let's see, she's right. So it's 3 times 2 squared, okay? So then plus 1. So 2 squared is 4 times 3 is 12 plus 1, 13. Perfect. What about f of 3? Somebody else. What did you get for that value? Adriana, thank you. What did you get? Plug in a, do what?
a really big number.
A really big number? I don't think it's that big. Let's see. We're going to put in 3 squared. Okay, so what's 3 squared? Got to do our exponents first. Remember, order of operations. Now, if you got a really big number, you might have said 3 times 3 is 9, and then 9 squared is 81. So you don't want to do that, because you got to raise 3 first. So 3 squared is, 3 times 3 is 9, yeah. So anytime I square something, I'm multiplying it times itself. If it's to the 3rd power, times itself 3 times, or times itself however. So this is 9 times 3, which is,
Wait, that's not.
20, what? 27. Yeah, plus 1,
Oh.
28. Right, so my third term, 28. Yes, ma'am. You know the last one? Okay. Okay.
49.
All right. So what is it?
49.
49. So I'm going to say she's right, but I'm going to go ahead and double check her just to make sure. So if I put a 4n squared, that's 16. 16 times 3, 48 plus 1, 49. Yep. You're right on. So those are the first 4 terms. Is that hard? No. And I could write each one of those just like I have here. I could say, f of 1 equals 4. But I also could write that as subscript notation. I could say a sub 1. Okay, 1's the same thing in that subscript as my function notation, meaning this is the first term is 4. And if I wanted to write the 4th term, I could write it this way too. A subscript 4 is 49. Either way is okay to write that. In fact, you're going to see it both ways on tests and quizzes and EOCs. You're going to see it in both ways, but they're the same thing. Now, let's talk about a recursive rule. Now, a recursive rule defines the nth term by relating it to a previous term. Okay? Now, a recursive rule means that in order for you to go forward, you have to have the previous term. Shaylin said a minute ago when she said, I was glad she said it, because when we're talking, I think I asked for the 20th term, she said, well, I have to get all the terms up to 20. Well, with a recursive rule, that would be true. That's why I like the explicit rule better. I just go to the term I want, okay? But this is an example of a recursive rule. Check it out. What we've written down here is f in a recursive rule, we're going to say f of 1 equals 4. In other words, I'm going to tell you what the first term is. I don't have to do that with an explicit rule. But in a recursive rule, I've got to tell you where to start. Have to. Because if every term is dependent on the previous one, that means I have to know where to start before I can go to the next term. So from the recursive rule, you're always going to get f of 1 equals 4, or it might be given to you either in the other notation, a of 1 equals 4. It doesn't really matter. But you get the first term. So the first term is 4. Okay? This rule now means that after the first term of the sequence, every term is the sum of the previous term. All right? So here's how it works. This is my recursive rule. Okay, and check it out. That recursive rule is f of n. I told you what the first term is. F of n is going to equal the function of n minus 1. What that means, f of n minus 1 means the previous term. Let me show you how that works in just a second, okay? So, if I asked about f of 2, okay, then f of 2 then is equal to the function of 2 minus 1 plus 10. In other words, what I'm saying in there, when I say 2 minus 1, that would be f of 1. What is f of 1? It is 4. That's the previous term. Now, I honestly think recursive rule is kind of confusing.
Yeah, this is really confusing.
But it's not as hard as it just looks that way. Because what the recursive rule says is I've got to have every previous term to get the next term. And what's happening each time is that each term I'm adding 10. That's what it says when I say plus 10 here. For all my n's will be greater than 1. So I'm going to give you f of 1, and then you got to figure everything else out. But you have to do it in order with the recursive rule. So we said that 2 minus 1, that's f of 1. F of 1 is 4. So now it's 4 plus 10, which is 14. The good news in the recursive rule, I've got the term. If I add 10 to it, I get the next term. And if I add 10 to that, so each time with the recursive rule, I'm adding 10. But I can't find anything in the recursive rule unless I've used every term and showed you every term. You know, if I wanted the 20th term using the recursive rule, I've got to do what Shaylin was saying, and I got to know what the 19th term is before I can find the 20th term. That's why I don't like the recursive rule. I like the explicit rule so much better. That's just my own personal preference. They don't really.
Wait, how did you get the 4?
Because, okay, remember what's 2 minus 1, right? That's f of 1, right?
Yeah.
What is f of 1? 4. It's given to you. Yeah, so each time you've got to go back to the previous term. That's what the n minus 1 here means. It means go back a term and then add 10 to it. It's not as hard as it just looks. Okay? So if I'm finding these, then I need to know, okay, here's what is f of 1 plus 5. F of 1 plus 5 is 4 plus 5, or 9. Check it out, okay? So here it's f of 3, so I need to know what is f of 3 minus 1, so I need to know what the previous term is here. And the previous term was 9, so now it's 9 plus 5. This is a different function, incidentally. And 9 plus 5 is 14. All right, so just check out the chart that I've given you there in your notes. I just keep referring to the previous term. I'm trying to find the fourth term now, and I look at the third term. The third term was 14. 14 plus 5 is 19. The good news is, in finding those values, all I'm doing with the recursive rule here is adding 5 each time.
Let's look at the homework. So what if there's like f equals like, you know how it's like f parentheses 1? Like what if it doesn't have that? Would you just like start like 1, 2, 3, 4? Or
It's going to give you the first term on the homework.
okay, because it says
Okay, unless we're using the explicit rule. Okay, so the explicit rule, you just plug it in. If it's a recursive rule, then you have to have the first term. Theoretically, you could work your way backwards, and you may have to do that at some point. So the first 4 terms of the domain of the function, I kind of got ahead of myself, 2, 3, and 4. So the domain's just each term number, okay? And the first term of the sequence we've said was right here that it is 4 in this problem. So kind of have 2 problems there.
so at the very beginning of this,
Yes.
it's like the same chart right here. Would
Yes,
you have to put 2 and then 3?
Yeah.
Like that? Oh lordy.
Bless your heart.
So we
All right, let's look at one more example, and then I'll give you a chance to begin your assignment, okay? All right, so this time we're going to take it a step farther and we're going to graph our sequence, okay? First of all, a movie rental club charges $20 a month plus a $5 membership fee. Now this is the explicit rule. I kind of like that one better. Use the explicit rule, f of n equals 20n plus 5. Complete the table to represent the charges paid for 6 months. So I need to create a table. I'm just going to do a T-chart. Okay. And I need to put in n and f of n. So here's the question. What are my values of n with the sequence? What are my input values?
1,
Yes, Shaylin got it right. The next one will be
2,
3, 4. It's just the position number of the
Would you ever
terms.
go to 5 or just 4?
It says for the first 6 months. So we're going to go 5, 6. All right. So depending on what the problem asks me. Okay. And we're plugging it in to this function. So if I input a 1, I get 20 times 1 plus 5, which is 25. If I input a 2, it's 20 times 2 plus 5. So 20 times 2 is 40 plus 5, so 45. 20 times 3, which is 60 plus 5, which is 65. What's happening here in my sequence? What do you see happening? It's actually gaining by 20 each time, isn't it? And so, and that makes sense because they charge $20 a month. 20 times 4 is 80 plus 5, 85. 20 times 5 is 100 plus 5, 105. 20 times 6 is 120 plus 5. So the last one's 125. Now, in your teacher-made assignment, there's a way to graph right on the graph there. And Kiara found it. I discovered it yesterday. All you have to do, and she can help you with it as well as I'll be happy to help you with it as soon as she shows me how. I know it's doable. I'm just not sure exactly how you do it. But all you have to really do is go in there and draw on the graph, and you can do it on that paper, and then you won't have to make a picture and submit it or anything. It'll all be right there.
It is very hard to draw on the graph.
It may be hard to draw the graph. And the other thing I did is I put a Google slide in there for you if you'd rather graph them on the Google slide by dragging the little points across.
It's so weird, like
Yeah. Yeah, and I came up with that yesterday after class was over, and then a couple of you had issues with it, and we were worked through it. Thankfully, I had trouble getting the little dots to drag across first time, but then they did finally drag, so that was good. So anyway, let's graph this right quick. Okay, so our x-axis is also the axis we have for months, or it is the position term of our sequence. And our y-axis is then our function. And so 125, so this is between, and obviously this is not going to be super accurate because halfway between 20 and 40 is 30. So 25 would have to fall right about there. I think it's a little bigger. Right about there. Okay, and then 2 and 45 is going to have to fall right about here. 3 and 65 will have to fall right about here. 4 and 85 fall about here. 5 and 105 will fall right about here. And 6 and 125 fall about. By the way, when I graph that, what do you notice about the points on the graph? They're discrete. We know that from yesterday. What else do we see there?
They're lined up.
They're aligned, aren't they? And they're all in a straight alignment. Now that will only be true in certain functions, and in fact, we'll look at those. We'll call those linear equations. But arithmetic sequences, which is what we're going to dig into a little more tomorrow, will always graph in a line. All right. So your assignment is due tomorrow, and you've got a few minutes here to work on it in class. Is H6, you'll find it in your classwork. And you also can use a Google slide to do your graph if you'd rather, or you may do it right on the handout itself on H6, or if you'd rather do it with pencil and paper, you can submit a picture. Any of those ways are fine. So go ahead and get started. You have a few minutes to work on that. If you have questions, please ask.